Hi, I'm Yunfei Ouyang. This is my CSC417 final project on 2D stable fluids. Back in 1980s, fluid simulation were very expensive and cost-heavy. In 1999, George Stam published a highly influenced paper about fluid dynamics called Stable Fluids. It proposed a stable solver to the incompressible Navier-Stokes equation in real time. His solver is based on the incompressible Navier-Stokes equation, where V is a kinematic viscosity, rho is a density, and F is an external force. Next, move on to the specific of Navier-Stokes equation. Joe Stam proposed a stable solver from manipulating the Navier-Stokes equation using the following decomposition. For arbitrary field W, it can be decomposed into the following form, W equal to U plus grad Q. Note that since U is divergent free, we define the following projection operator, apply it onto the equation in the previous slide. This is the equation we are going to use to implement a stable fluid solver. Next is the density field of the fluid. For an arbitrary scalar field A in the fluid, the update of A can be described similarly as the following, where K is a diffusion constant, alpha is a dissipation rate, and S is a source. So finally, we can start implementing the solver. First, we need to have a 2D grid representation. Given length n, our grid will have size n plus 2 times n plus 2. The extra 2 layers are used to redirect the fluid, which means that the setup allows a fixed boundary condition for the fluid. The grid will act like a box where fluid cannot leak out. To understand how the solver works, we need to take a deeper look at the equation on the right. Note that they are very similar because one is for the velocity field and another is for the density field. There are 4 parts for the solver: add force, diffusion, advection, and projection. We will explain them one by one. First is to add force. Since we are implementing an interactive fluid simulation, we need a way to add a force from the user's mouse motion. Since a mouse can click and drag, we decide to let a mouse click be adding a source to the scalar field, and mouse drag to add velocity in the velocity field. The next part is diffusion. Note that diffusion doesn't depend on the velocity of the fluid, whereas it's a net movement of anything generally from a region of higher concentration to a region of lower concentration. In our 2D grid, we consider the grid cell separately, where each grid will be updated by becoming the average of the grid cells surrounding it. To avoid overshoot of the basic linear interpolation, we adapt the Gauss-Seidel method to make the diffusion process stable. Advection is the transport of substance or quantity by the motion of the fluid. Note that it's very hard to update cells forward in time since the particles will not always lie in the center of the cell. Instead, we can trace particles that lie exactly in the centers of cell and trace them backward to find the starting location. The linear interpolation is used to calculate the previous 2 times 2 grids density to the new density. The linear interpolation step is defined as follows, where S is the current substance, G10, G11 are the bottom 2 grid, G00, G01 are the top 2 grid, IX and IY are the ratio between the 2 times 2 grid. Last is the projection. The projection method is an effective means of numerical solving time-dependent incompressible fluid flow problem. It ensures that vector field is mass conserving. Note that it's achieved by using the previous decomposition. We see that U is divergent free field, where we want to get it by subtracting Q from the vector field, W. Mathematically, we have the following formula, where the Gauss-Seidel is used to solve Q, and we can get the gradient of Q and finish the projection. The last thing is the update. We update the velocity field and the density field separately, where the velocity field depends on the viscosity constant, and the density field depends on the diffusion rate. Here are the steps for updating. Note that for dissipation alpha, we simply divide the density field by the dissipation rate, 1 plus dt times alpha. Finally, here are some results. Thanks for watching. Have a great day.